Okay. Uh, Welcome back, everyone. So let's begin from where we left in the last session. So what we were discussing in the last session was the linear stability analysis of inviscid parallel flows, and we argued that this analysis can also be extended to nearly parallel flows, and uh, and we begin by trying to understand what motivates us to study linear stability analysis, and thereafter we saw certain examples of so as to where stability basically comes into the picture. Stability meaning instability of fluid mechanics come into the picture, and and then as an exercise we looked into this problem where there was a fluid whose base flow was given by a base velocity, which is u of z, and a base pressure, which is pv. And the question that we and of course this flow is inviscid in nature, meaning that the viscous effects are not present. And given that, the question that we try to answer is that if we add some perturbations into this base flow, will the perturbations grow with time or decay with time, or there is something which is known as marginally stable, that is the perturbations which just remain, they will neither grow nor decay, and sometimes these kind of perturbations are called marginally stable perturbations. But yeah, so the question that we seek to answer is that what will happen to these perturbations if they are added to this base flow. Now what we did is, we looked into the regime of linear stability analysis, where we say that the magnitude of the perturbations is very much less than the magnitude of the base flow. That is, the perturbations always remain subdominant with respect to the given base flow that we have. And with that, we started off with our governing equations, which we wrote it for the aggregate dimensional variables, which was nothing but the continuity equation, the Euler's equation. And and then what we did is we decomposed the aggregate variable, that is the total variable, into the base variable plus the perturbations. And thereafter, we non-dimensionalize our governing equation uh, by choosing certain scales of our problem. For instance, we choose the length scale to be the channel height, the characteristic scale for velocity to be either the maximum of the base velocity or the average of the base velocity. It actually doesn't matter which characteristic scale you take. And then we define the advection time scale of our analysis also with the scale for pressure, which was the advection scale for pressure, which is rho times of the characteristic velocity squared, is what the advection scale of pressure is. And then using all these characteristic variables, we formally define the non-dimensional variables of our analysis. And what we did is we plugged in these non-dimensional variables, as we always do, and as we had been doing repeatedly in our analysis, that we define certain characteristic scales, we write the non-dimensional variables, and then substitute the non-dimensional variables into the dimensional governing equations to get the non-dimensional governing equations. So, so in doing that, what we wrote is we wrote the governing equations which were satisfied by the aggregate, this time the non-dimensional variable. For instance, the total velocity is given by v, the total pressure field is given by p. But remember, now this v and p, and also all this time, all other, like, what to say, independent variables like time and distance, these are all now non-dimensional. Okay. And the similar mechanism we wrote for the aggregate variable, albeit now for non-dimensional, in non-dimensional form, is that it comprises of the base variable plus the perturbations. And then what we did is, this is one of the important aspect of linear stability analysis, is that we this uh, substituted this form of the aggregate variable into the governing equations which they satisfy, and then derive linearized equation for the perturbations. Because we know that the base law trivially satisfied the governing equations, which we proved it in the last class. This enabled us, using the staying in the regime of linear perturbation analysis, to discard the nonlinear terms, and then come out with equations which only the perturbed variable satisfy, but those equations are now linear, because we are in the regime of linear stability analysis. And equation 5a and equation 5b were the two equations that we derived after linearizing the the equations that we had at our end. Okay, so as I said, equation 5a and 5b are the linearized governing equations that the part out variable v dash and this would be p dash, that the part out variable v dash and p dash satisfy, where you can write the part out variable in terms of its components in x, y, and z form. Okay, and then what we did is we wrote this equation into its component form, and when we wrote this equation into its component form, we basically got our x momentum, y momentum, and z momentum equations, which the perturbations satisfy. Okay, where remember this u of z is the velocity field of the base flow, which is already known to us, and thus this term u of z times del u del small u dash by del x is a linear term, because of the fact that this u of z is, because this u of z is known to us, or in other words, the complete information of the base flow is known to us. Okay, and that's why you can appreciate that this equation 6a, 6b, and 6c, these are all linear, coupled with the continuity equation, which is equation 60. Okay, now thereafter we did one even more important analysis, which is writing the perturbations, that is writing the perturbed variable, for instance the x direction velocity, the y direction velocity, the I'm sorry, z direction velocity, and the pressure in terms of its normal mode. Okay, for instance, the x direction velocity u prime can be written as u hat of z times e power sigma d plus the plus I times kx plus ly, where we saw that this kx and k, this k and l, this k and l were generic wave numbers, and I so we argued that there is essentially an invisible integration taking place over this wave number dk and dl, but since we are performing a normal mode analysis, meaning that each and every mode, or so the term wave number and mode, these can be used interchangeably, and sometimes I will speak I'll tell about wave numbers, and or sometimes I will call the wave numbers and mode, but please don't get confused. These wave numbers and modes, these are just the same terms, uh, which may be used interchangeably. Okay, so the idea is that since in normal mode analysis each mode operate independently with respect to one another, we can discard the integration sign and then write this for any generic mode or generic wave number k and l. Okay, now we also argued uh, on what basis do we choose the normal mode, and why is this form of normal mode considered. Okay, if you missed this discussion, you can go back to the previous video and check it out, but yeah, you need to understand this, and you need to understand the essence of writing the perturbations into its normal modes. Okay, where we say that this sigma is essentially, which we call it as the eigenvalue, or this is the term which dictate whether the perturbations will grow with time or decay with time, and this uh, I would say this term sigma uh, controls the growth rate of the perturbations. Okay, this is something that we also like kind of discussed it in the last class. So that's it. Then we also wrote the other velocity components, for instance the y velocity component and the z velocity components in terms of its normal mode and also pressure. Okay, now what we did is, for this analysis, and also I believe you have done this same kind of trick when you derive the Ohrs-Sommerfeld equation in the lecture classes. What you did is you wrote sigma, which was my eigenvalue, which obviously dictates the growth rate, as some I alpha times c, where now c, so this is just a transformation that we did, where now c is my new eigenvalue, and alpha is just replaced by, and k, that is the wave number in the x direction, the generic wave number in the x direction, that is replaced by alpha, which again can be interpreted as a wave number in the x direction, and l is basically replaced by beta. So it's just a transformation that we are doing. You can carry out this problem. You can solve this problem without even doing this transformation, but because of the fact that many textbooks just follow these kind of notations and they have used this transformation, this is something that I have also followed here. Okay, so what we did is we ended the last class by you know trying to see what by basically trying to see how c controls the growth rate, that is how this eigenvalue controls the growth rate. And then what we did is we wrote c as a, since c is an eigenvalue, It can be real, it can also be imaginary, it can be purely real, or it can be purely imaginary. All of the, I mean, all the options are possible. And then what we did is we wrote C as a real part and an imaginary part. And then when we substituted, we saw that the condition for stability came out as follows. So the condition for stability was that real part of, sorry, the imaginary part of Ci has to be 0 if there are perturbations, but if these perturbations decay with time, then the necessary condition is that Ci has to be less than 0. On the other hand, the condition for instability, which means that if there are perturbations that are present, if they are present, and what will happen in an extended period of time, if the perturbations will grow, then the necessary condition is that Ci has to be greater than 0. So these are the two things that we saw, and this is where we ended our discussion in the last class. And we will now take it up from here, because we are yet to fundamentally, derive an equation which essentially governs whether this, which essentially will govern how this, how these perturbations actually behave, and and in the end, the eigenvalue, that's the last part that we need to do. So what will be the eigenvalue that we are supposed to get, is something that we will see today, and we will derive the famous Rayleigh stability equation, as you guys know, uh, which governs stability of inviscid parallel flows, and we will do this by taking up from where we left it in the last class. Okay, so I'll stop here for a couple of minutes. If you have any questions or if you have any suggestions, you can ask, or else we will proceed with from here, like we'll proceed it. So I hope you can appreciate that. Now what we need to do is, since we have established the perturbation in terms of its normal mode, what we need to do is we just need this to substitute it into the governing equations of the perturbations, for instance the x, y, and z momentum equation, to basically get equations which so in other words, what we are doing is we are kind of converting the PDEs into an ODEs, and this is something that we will see when we substitute the normal modes into the linearized governing equations which govern the perturbations. Okay, and then thereafter we'll see a very famous theorem which is known as the squares theorem, and we will see we'll take it up from that point. Okay, all right. So I'll stop here for a couple of minutes. If you have any questions, you can ask, or like I'd be happy to take any suggestions. Okay. Okay, so let's start the next step. So the next step is, so what did we do? So what we did is we wrote the perturbed variable, the x, y, and z momentum, x, y, and z direction velocities and pressure in terms of its normal mode, and then what we did is we did this transformation basically. Okay, so what we'll do is, if we substitute, so the next step is obvious. What we need to do is we'll have to substitute the normal modes. So what we'll do is we'll substitute the normal modes in the linearized governing equation for disturbances. Okay, and which means what we are doing is we'll be substituting this 7a, 7b. So what we're doing is we'll be substituting this 7a, 7b, 7c, and 7d into equation 6, basically 6a, 6b, 6c, and 6d. That's what we are going to do. So what we'll do is we'll substitute equation 7, uh, which comprises 7a, 7b, 7c, and 7d into equation 6, which means into 6a, 6b, 6c, and 6d. So if we do that, it's just substitution. So I'll just skip the algebra here. So if we do that, the continuity equation becomes, just for the sake of time, I'll just skip the algebra. You can do this. It's just a mere substitution that you need to do, and you can just very nicely do it at your end and verify. So what you can do is, or what you can see is the continuity equation, which was del u prime by del x plus del b prime by del y plus del w prime by del z equal to 0. This was our linearized continuity equation. This will turn out to be I times u hat of z alpha plus I times beta v hat of z plus dw hat by dz equals to 0. So this is what you will get when you substitute the normal modes of u prime, v prime, and z prime into the continuity equation. Okay, and that is obvious. See, the this e power term will get cancelled, and if you want to see what is del u prime by del x, you will just get an ik that is coming out, or it will not be ik because we have done this transformation that this sigma is minus I times c alpha, and that's the reason why you see an I and an alpha coming out in the in this form. Okay, I hope the logic is clear at this point. It's just a mere substitution that we are doing, and I hope this is not of a big task at your end. Okay. All right. So this is the continuity equation. So this is what the linearized form of the continuity equation would look like if we substitute the normal modes into the linearized equation of the perturbations. Okay. So let's name this equation by some other name. So I'll just name it as, let's say, equation 8a. And similarly, if you do the same exercise for the x momentum equation, what you will get is you will get I alpha u minus c times u hat of z plus w hat times du by dz is equal to minus I alpha p hat of z. Again, the logic is clear. Use the transformation and then substitute the normal, use the transformation in the normal mode, and then just substitute the normal modes into the governing equations or into the linearized governing equation of the perturbations. Okay, and I name this as equation B, and so this is the x momentum equation. So this happens to be the continuity equation. This is the x momentum equation. So the y momentum equation turn out to be I alpha u minus c v hat of z, and this is I times beta v hat of z. This is the y momentum equation. I'll write it at equation 8c, and then also I have the z momentum, which is I alpha times u minus c times w hat of z equals to minus of dp hat by dz. Okay, so these equations, equation 8a, 8b, 8c, and 8d are a result that you get. So these equations are a result that you get when you substitute the normal modes of u prime, v prime, w prime into the linearized equations, which is equation 6a, 6b, 6c, and 6d. Okay, and of course you need to do this transformation as I have said before. All right, I'll again stop here for a couple of minutes, and now what we'll do is we will see a very powerful theorem which is known as the squares theorem. Although we'll not prove this theorem, you can prove this theorem very easily, but we'll not do this at this point. But if you're interested, you can post this in the discussion forum, and I will provide you the proof of the squares theorem in a separate note there itself. Okay, but we'll not prove this, but we'll visit the squares theorem, and then we'll apply the squares theorem into our current analysis. Okay, but before that, if you have any questions, you can ask. So I believe you are with me so far, that whatever the steps that we have been doing, I hope that is clear to you. And although we are solving a very generic problem of stability, but trust me, for linear stability analysis, it is the same algorithm that follows in whichever problem you basically solve, be it a multi-fluid, be it a fluid with multiple interfaces, or like fluid interfaces, or like a single fluid, or like a viscous fluid, or whatever stability problem you are working on. But remember, this is only true if you're in the regime of linear stability analysis. Okay. All right. So now what we will do is, so I hope you have, I hope you realize that what we got is, we got, so these, so you can appreciate that these are ODEs. So upon substituting the normal modes into the equation which is satisfied by the perturbations, which are PDEs, what we knowingly or unknowingly did is, we converted that PDE into some ODEs. For instance, this is an ODE, as you can appreciate. This is also an ODE, and I understand, of course this is an ODE, but this is a linear ODE, as I said. And of course these are also ODs that you can that of course you can verify very nicely. Okay, so that is what we get when we actually substitute the normal modes into the governing equations. And I hope you can appreciate that. So now what we'll do is, we'll apply the famous theorem which is known as the squares theorem. Okay, and what squares theorem says is, so I'll write down the statement, although I'll not write down verbatim, but I will write for the ease of understanding of the audience. So what squares theorem says is that for inviscid flows, but I'll write down it in bracket that it can be extended to viscous flows. So what squares theorem says is that for inviscid flows, but you can extend the same theorem into viscous flows. What it says is that for inviscid flows that are parallel or nearly parallel, to the disturbances are stronger than their 3D counterparts, provided, this is important, provided the wave numbers are same. Okay, so this is what actually the squares theorem means. Okay, so what does it say? It says that for inviscid flows, but although you can extend this for viscous flows, and if the flows are parallel or nearly parallel, then the 2D perturbations are stronger than their 3D counterparts, provided the 2D perturbations and the 3D perturbations have the same wave number. Okay, so what it means is that if there is a perturbation, and if that perturbation is unstable, then it is sufficient to study the 2D problem and realize its stability, rather than solving the entire 3D problem and looking for whether the perturbations grow or decay with time. I agree that if you want to get the total flow field of the perturbations, then you need to solve the 3D equations, because if you have a 2D equations, you will miss out basically in one direction. But our objective is not to get the total flow field of the perturbations. Our objective is to see that in a given flow of this type, if my perturbations if there are perturbations, my objective is to see whether these perturbations grow with time or whether these perturbations decay with time. So in that context, it suffices to just study the 2D problem, because according to Square's theorem, it says that the 2D disturbances are much stronger. So if I study the 2D disturbances, and I find that my perturbations are basically basic, so and I find that there are instabilities, and these instabilities are growing with time, then I can guarantee that in the 3D problem also the instabilities will also grow with time, because the 2D perturbations are stronger. Okay, so this is what Square's theorem essentially says. So now you can ask me that so what? So what is the problem, or what is the remedy if I just solve it, if I just study the 2D problem? See, the 2D problem, I hope you can understand. The 2D problem means that we are discarding discarding one direction. For instance, in this problem, what we'll do is, if we just apply the Square's theorem, I hope you can realize that we will just consider perturbations into just the x and the z direction, meaning that this v prime will not be present. That is the perturbed velocity, let's say in the y direction, this will not be present. We cannot discard the z direction. That is simply because the base flow is varying along the z direction. Okay, but what we can do is we can discard the y direction, and it just suffices to just consider perturbations, let's say u prime, w prime, and just p prime. Okay, that means we have reduced the 3D problem into a 2D problem. So the advantage of reducing it to a 2D problem is that, first of all, the number of governing equations will come down, and since the number of governing equations will come down, the number of unknown variables will also come down. And then we can use the famous stream function approach to basically reduce the unknowns. So there are two unknowns. I hope you can understand that the unknowns are basically u prime and w prime. So if it's a 2D problem, my unknowns becomes u prime and w prime. What I can do is I can define a psi prime, which is the perturbed stream function, and then we can reduce this u prime and w prime into just one unknown, which we all know. That is, we will just simply follow the stream function vorticity approach. Okay. So the advantage of this 2D disturbance is that in 3D, the number of unknowns were 4, that is u prime, v prime, w prime, and p prime. By applying Square's theorem, we have reduced the problem. We have reduced the 3D problem into the 2D problem, and then since now we have the 2D problem, we can, so it's a 2D, since it's a 2D problem now, we can use the stream function to further reduce the number of unknowns, which was u prime and w prime, that is the velocities, into the unknown stream function psi prime. And that's the reason why the Square's theorem is essentially very powerful. Okay. Number two, I hope you can understand that if someone asks me that what will be, and I have said this statement before also, that no, I don't just want to. So if someone says to me that no, I just don't want to assess the stability, I want to get the complete picture of the perturbation flow fields. That is, I want to get u prime, v prime, and w prime. Then there is no use of applying Square's theorem, because Square's theorem will only give you u prime and w prime. It's a planar problem that we are solving for. But since now our objective is not to get the entire flow field of the perturbed variable, but to see whether if there are any perturbations that are present in the flow, they will decay or grow with time. It just suffices to study just the 2D problem, because by Square's theorem, it says that the 2D disturbances are much stronger than the 3D disturbances, provided their wave numbers are equal. And now we will see what does it mean by saying that their wave numbers are essentially equal. But I hope this logic is clear on on why on what is the benefit essentially of reducing it to a 2D problem. Okay, so the line when I say that hold on, yeah, okay. So the line when I say that the wave numbers are equal, it means that, let's say I define a 2D wave number which is alpha tilde. What it means is that the 3D wave number, let's say I define it as alpha tilde 2D, then the 3D wave numbers which are alpha 3D and beta 3D, if you remember, because these are the two wave numbers that we defined, right? If you remember, these are the two wave numbers that we defined. It is just I times of alpha x plus beta y. That is what we define, where alpha and beta, or this k and l, because this k and l were nothing but just alpha and beta, and these were the two wave numbers. So what it means is that for Square's theorem to be valid, my alpha 2D, that is the magnitude of alpha 2D, this should be equal to square root of alpha 3D squared plus beta 3D squared. This should hold good at all times. Okay, this should be valid. Okay, see, and it of course makes sense. You know why? Because what we did is we wrote the perturbations as something like this. So it was e power sigma t plus I times kx plus ly. It was something like this. Okay, and then what we said is my sigma is nothing but minus of I times of alpha times c. I think this was how we defined sigma, and then my k was alpha and my l was beta. Okay, so what I can do is I can just write this as e power sigma, which is minus I times of alpha times c times t. Will not bother this, and this term I can write it as I times of some k vector dot x vector, where this k vector is essentially known as the wave number vector, or it's so I hope you understand that this is a vector, and this is known as the wave number vector. where this wave number vector can be written as alpha times, because of the fact that my k is equal to alpha and my L is equal to beta, this wave number vector can be written as alpha times Ex, or I'll write one more step for you to be clear. So first you can write this k vector as some Kex plus, or let's not name it as k vector because it will confuse you with its components. Let's name it as what? Maybe let's name it as what? Okay, I can name it as lambda, let's say. Okay, so let's say this lambda bar is the wave number vector. So I can write this lambda bar as Kex plus Lui, and then my x bar, which is the position vector, is just Xex plus Yey. Okay, so whatever you saw here is essentially the dot product between this between this lambda bar dot x bar. And now I say that for the 2D disturbance, so I hope you appreciate that for 2D disturbance, my lambda 2D will just be equal to, and oh, okay, I just missed one step. I need to write this as alpha times Ex because my k is equal to alpha, and this is beta times Ey because my L is equal to beta. And then what I say is that for lambda 2D, I'm just considering a 2D disturbance, which means that for 2D disturbance, the y these terms will not be there, which means I'm just writing it as what? I'm writing it as alpha tilde 2D times Ex. Now you need to understand this is alpha bar 2D. Now you need to understand that for these wave numbers, wave numbers, this and this wave numbers to be equal, it must be that the magnitude of this has to be equal to the magnitude of alpha 2D. And that's the reason why I say that alpha tilde 2D should be equal to square root of alpha square plus beta square. Okay, and this condition must hold good if you are trying to apply the squares theorem. That is, I repeat, and physically it should also make sense that for the given 2D disturbance that you have considered, its wave number should be exactly same as the wave number of the actual 3D problem. Okay, and then you can reduce your 3D problem into a 2D problem, as we will do very shortly. All right, so I hope the squares theorem is clear. So then what I can do is so now what? So now what we'll do is we will, instead of writing the entire 3D problem, we will now change the 3D problem into just the 2D problem. So the 2D problem becomes, so what will we have? So we have the continuity equation. Okay, the continuity equation. So what was the continuity equation? It says that del u prime by del x plus del v prime by del y plus del w prime by del z. This is equal to 0. But we know that we are in the 2D problem, so this term is not present. This term is not present since we are dealing in 2D flow. We are in the 2D problem. Which means if you substitute now, so then what does it become? So then I hope you can understand that your normal modes, which were basically u prime, which was u prime of z e power, what was it? It was so what was the normal mode that we wrote? It was, okay, e power minus I alpha t. So it was e power minus I alpha ct plus I times of alpha x plus beta y. But we know that it's just a 2D problem, so I just don't have this term. So this means that my normal modes now, u prime is equal to u prime of z e power what can be, so it is I alpha ct plus I alpha x, and then I can just write it as u prime is equal to u hat of z times e power. If I take I alpha common, it just becomes x minus ct. Okay, so this is the reduced normal mode when I just consider the 2D problem. So this is the normal mode if I just, or in other words, this is the normal mode if I just consider the 2D problem. Okay, so this is u prime. Similarly, since I just need the z direction, I mean the z part of variable, so the w prime in the similar sense can be written as w hat of z e power I alpha x minus ct, and pressure p prime can be written as p hat of z e power I alpha x minus ct. Okay, all right, I hope this is clear at your end. Okay, so I'll name this, maybe I'll name this as some equations, maybe I'll name it as equation 9a, 9b, and 9c, where you must understand that this alpha, I repeat, this alpha, so this alpha that we wrote, this is not the alpha of the 3D problem, this is essentially alpha tilde 2D. Okay, which is nothing but the wave number of the 2D problem. But for the sake of repetitiveness, I'll just consider that alpha tilde 2D, I'll just represent it as alpha, basically. This is just for the sake of not writing alpha tilde 2D repeatedly, I'll just call it as alpha. But you must be careful that this alpha is not the alpha of the 3D problem. This is the alpha of the 2D problem that we have reduced the problem into. Okay, because remember, alpha tilde 2D is not equal to alpha. In fact, alpha tilde 2D is equal to square root of alpha square plus beta square, where that alpha and beta were the individual wave numbers in the x and y direction in the 3D problem. Okay, I hope this is clear. All right, so now, so 9a, 9b, and 9c are the normal modes for the 2D problem. And then what you do is just write down, so we have the linearized governing equations. What you do is in the 2D problem, substitute these normal modes. So the next step is substitute these normal modes into the linearized governing equation for the perturbations, for the 2D perturbations, I would say. So what you now need to do is what what you now need to do is you need to start from first, define the aggregate variables. Okay, write your variable, write your two. So now remember, there will be two variables, u prime and w prime, and then and also p prime, of course. There is pressure, and then what you need to do is you need to write your aggregate variables, which are now 2D, as sum of the base variables plus the perturb variable, and then substitute this form into the governing equations of the aggregate variable to get the linearized governing equation of the perturbations, and then substitute these normal modes into that linearized equation of the perturbations, which are now 2D. Okay, but trust me, the good thing is what you will find out is that your equations will be exactly same as your 3D equation, just that these terms, the terms in the y direction will not be there. And this is common sense. If you do that, you will realize that this is indeed true. Okay, so what I'm saying is that you start with a 2D problem, write the aggregate variables. Your aggregate variables will be your velocity in the x and z direction and your pressure, and then define the base variables which you already have. Do this, whatever we did, do the non-dimensionalization and all these things, and then write down the governing equations of the aggregate variables in non-dimensionalized form, and then write your u, w, and p as your base plus the perturb variable, substitute that form, and then get the linearized equation for perturbations. And then what you do is use the form of the normal modes of the 2D variables, which is u prime, w prime, and p prime, and then substitute it into the governing equations of the 2D perturbations to basically get the ODEs. But my point is that when you do this exercise again, just how we did, you will appreciate that you will exactly get these equations. That is equation 8a, 8b will, so that is equation 8a, which is the continuity, but you will not have this term. Similarly, you will get the x momentum equation, and y momentum equation will just be redundant because it's now a 2D problem, and similarly, you will get the exact z momentum equation. But again, remember, the only difference is that this alpha, which was, so in equation 8a, 8b, 8c, and 8d, this alpha was the wave number of the 3D problem. The only difference you will get here is that this alpha that you will write in the 2D problem is essentially the wave number of the 2D problem, which is in magnitude is equal to the square root of alpha 3D square plus alpha plus beta 3D square. I hope you are clear with me on this point. So you can do this at your end, the steps that I have said, and you will appreciate that you will exactly get the same equations as of these equations 8a, 8a, 8b, and 8d. With this term obviously will not be there because it is now a 2D problem. Okay, so what you will get is you will exactly get this equation. So if you substitute this form of the normal modes, okay, into the linearized governing equation for a 2D perturbations, as I said, so what you will get is the linearized ODEs for the 2D problem are. So this is what we'll get. So the continuity will be I times u hat of z alpha plus dw hat of z by dz equal to 0. That's the continuity. And the x momentum, what's the x momentum? So the x momentum is I alpha u minus c u hat of z plus w hat times du dz. And this is equal to minus I alpha p hat, which is just a function of z, and the z momentum is I alpha. This is exactly the same equation that we wrote for the 3D perturbations. Okay, I alpha u minus c w hat of z. This is equal to minus dp hat by dz, and yeah. So as you can appreciate, we have reduced the four equations into 3 equations, but again and again I repeat that this alpha is essentially the wave number. This is essentially alpha tilde 2D, that is the wave number for the 2D problem. Okay, so this is the wave number of the 2D problem. Okay, all right. So you can appreciate that we have reduced the four equations into 3 equations, and let's name this. Let's name this as 10a, 10b, and 10c. Okay. All right. This is your continuity. This is your x, and this is your z. See, I hope you understand that why did we discard the y direction and not the z direction. So the answer is that since the base flow itself is varying in the y direction, and the direction of the base flow is in the x direction, so I cannot discard the x and the z direction. So the only option that I had in order to make my problem a 2D problem is that I can discard the variables in the y direction, because in y direction there is no flow and there is no variation of the flow. Okay, and that's the reason why we discarded the y direction and not the other orthogonal directions. All right, so what we now need, what we will do is, as I said, see, now we need to basically solve this. Okay, but what do we have to do? So since now we know that we have reduced the 3D problem into the 2D problem, we can use, I'll write down, we can use stream function approach. See, the advantage of using stream function is twofold. First, we will reduce the number of variables in the velocity from 2 into the stream function, which is 1. This is 1. This is the first advantage. The second advantage is that the manner in which we define the stream function, the continuity equation is automatically satisfied. It is trivially satisfied. So that's why we'll be using the stream function approach. So to this end, what we'll do is we'll define a perturbed stream function psi prime, and we'll write this perturbed stream function as phi of z, just how we use the normal mode analysis, as e power I alpha x minus ct. Okay, So this where I hope you can appreciate that this psi prime is the perturbed stream function, and phi of z is the so phi of z is essentially the eigenvalue corresponding to this perturbed stream function. Okay, and I hope you can understand that what does perturbed stream function essentially mean. So for instance, the base flow, for instance, for the base flow, the direction of streamlines, let's say, is in this direction. Okay, so this is the direction of streamline. Let's say I call it as psi base. So the perturbed stream function is that when the flow gets perturbed, psi prime would look something like this. It will have variations along time, and it will have variations along x, x as well. Okay, and z as well, of course. So this is essentially psi prime, which is the perturbed stream function to the given uh, stream function of the base flow. Okay, so this is your perturbed stream function, and this you can call it as base stream function, or something like this, base stream function. You can appreciate that this psi prime is a function of time, because the perturbations of course will be function of time, because their velocities are itself function of time, the perturbed velocities of I mean, and of course it's a function of z. It's also a function of x, on which location you are basically in. Okay. All right, so now what we need to do is we need to use the relationship between psi prime, u prime, and w prime to basically transform this equation into an unknown in the stream function. Okay, so we know, so this is easy, right? Because we know that my u prime, that the relationship between velocity and stream function, we'll use that. That is, my u prime is del psi prime by del z, and v prime is minus del, not v prime, this is with w prime, because we have two velocities, that is x and z, and this w prime is minus del psi prime by del x. Okay, and since we know that my u prime is what it is, u hat of z e power I alpha into x minus ct, and my w prime is equal to w prime of z e power I alpha x minus ct, which means if I use this relation, I can straightforward say that if I substitute this, then this is u hat of z e power I alpha x minus ct, and this is equal to del w prime by del z. So del psi prime by del z, where this del psi prime by del z will be d phi by dz into I alpha x minus ct. We just evaluate the derivative from here. That's what we are doing here. Okay, so this just becomes d phi by dz e power I alpha x minus ct, and this will basically cancel out to give you the relationship between phi and u prime of z, which is u prime of z is equal to d phi by dz. Okay, let's name it as 11a. Similarly, if you do this for the w component of velocity, similarly, if you do this for here, that w prime is equal to minus del psi prime by del x, what you will get is your w prime in terms of normal mode is w hat of z e power I alpha x minus ct, and then this becomes del x of phi of z e power I alpha x minus ct. So when you do this, what you will get is u hat of z e power I alpha x minus ct as minus I alpha times phi of z into e power I alpha x minus ct. That's just the differentiation that we are doing, and then this term will basically cancel, which means that you will now get a nice relation between w prime of z, which is equal to minus I alpha times phi of z. Okay, and this is your equation, sorry, 11b. Okay, so the next step is easy, because we already have the relationship between u prime, sorry, u hat of z as phi, and w hat of z as minus I alpha phi. So we will just substitute this into this equation. Okay. So I hope you understand that we'll replace this u prime, sorry, u hat of z, w hat of z in terms of phi by using equation 11a and 11b. So the next step is using 11a and 11b in equations in where, so we'll use this in equation 10 basically. Okay, all right. So if you do this, let's do this in equation 10. So what is equation 10? So the continuity, let's first see the continuity. Okay, so the continuity is what? The continuity is I alpha u hat plus dw hat by dz is equal to 0. But I know that my u hat is equal to d phi by dz. So it just becomes I alpha d phi by dz. I'll replace it as phi prime of z, where this phi prime is just d phi by dz. Okay, and then this becomes plus of this term, so this becomes plus of d dz of w hat, and w hat in terms of phi is just minus I alpha phi. It is just minus I alpha phi of z, which means what do we get? So we get I alpha phi prime as equal to minus I alpha phi prime, which is 0, which is equal to the right hand side. And this is obvious because the manner in which we define the stream function, it trivially satisfies the continuity equation, which means that if your aggregate stream function satisfy the continuity equation, your Perturb stream functions and all the associated variables of your Perturb stream function should also satisfy the continuity equation. And this is indeed what we get. Okay, so we'll write it down that the continuity is trivially satisfying. Okay, all right. Okay, then let's do this exercise for the x momentum equation and see what do we get. So if we do this for the x momentum, what do we get? So the x momentum equation was what? It was, so it is basically this equation is this. So it is I alpha times of u minus c u hat plus du by dz. I will write it as u prime just to make things a little bit simpler. And then this is w hat, where remember this is du by dz, and I'm calling it as u prime. Okay, and then this is minus I alpha p prime. And then if I substitute u hat and w hat in terms of phi, what I'll get is I'll get I alpha u minus c times phi prime, because of the fact that my u is equal to phi prime, and then w prime is equal to what? It is minus I alpha phi, so this becomes minus I alpha u prime phi, and this is equal to minus I alpha p prime. Okay, yes, I think this is fine. All right, similarly, if I do the same exercise for the z momentum equation, I'll not do this repeatedly now. You can easily verify that your z momentum. Okay, let's do it. So what was your z momentum? Let's do it. Let's not skip it now. So your z momentum is basically this. So you have minus I alpha u minus c times w hat equal to minus dp hat by dz. I will call it as phi prime, phi hat prime. Okay, the derivatives I'm just replacing it as prime to, you know, just for repetitiveness. Okay, and I know that w hat is equal to minus I alpha phi, so I can write it as minus I square alpha square and this is u minus c, this is phi, and then this is minus p hat prime. Okay, so this is your, so let's name this equation. This is your equation 12a and 12b. All right, I'll stop here for a couple of minutes. If you have any questions, you can ask. Okay, so I hope this all the steps are clear. Uh, just as a quick recap, what we did is we applied Square's theorem, wrote the normal modes for the 2D disturbances, substitute the normal modes into the linearized governing equations of the 2D problem, and then since we are in the 2D regime, instead of solving for two variables, we use the stream function approach, define the stream function part of stream function psi prime to the original stream function to the original base stream function psi b, and then wrote the part of stream function also in terms of normal modes, and then establish the links between the velocity and the link between the link between the eigenfunction of the velocities of the individual velocities component and phi prime. That's all that we do using the definition of the relationship. Using the relationship of stream function and velocities. That's all that we did. Okay. All right. So now the objective is to get an equation for phi. That's it. Because once we know phi, we basically know, once we know, so I hope you realize that these problems are an eigenvalue eigenfunction problem. So once we know the eigenvalue eigenfunction pair, we basically know everything. So the eigenfunction that we are solving for is phi prime. Okay, so that's the one thing that we will try. So in order to solve for phi prime, what we can do is we can eliminate the pressure. We can eliminate the pressure term as so. So this is exactly what we do in for stream function approach to basically get an equation for phi prime. So now how can we eliminate pressure from these two equations? That's the next task. That's the next task that we should think. So what we can do is, so the next step, let's say what is the number of this step. So this is step 7. So the next step I'll call it as step 8. So step 8 is eliminate p hat of z to get an equation. Remember, this will be a single equation of phi hat, or what we call, yeah, not phi hat, it's just phi of phi of z. So what do we need to do? So what should we need to do in these two equations to eliminate this p hat? So what we can do is we can differentiate this equation with respect to z. Okay, and we can multiply this equation, multiply the z momentum equation with I alpha. So what we can do is we can differentiate. So the x momentum will differentiate this with respect to z, and then we'll subtract the I alpha times the z momentum equation in order to eliminate this p hat from our equation. Okay, so that's what we will do. So what we'll do is we'll do ddz of equation, the x momentum is equation 12a. So we'll do ddz of equation 12a minus I alpha times equation 12b. Okay, equation 12b. Okay, that's what we will do. And if you do this, let's see what will you get. So if you do this, that if you differentiate the x momentum equation with respect to z, so let's see what do we get. Okay, so this term will give us what? So it is so let's use this equation. Where is it? Is it okay? So what we need to do is we need to just we just need to differentiate this equation with respect to z. So it will be what? It will be, so if we just differentiate this, it will be I alpha times u minus c, just use the product rule, phi double prime plus phi prime u prime. See, how do we get? Because see this, you need to differentiate. See, I alpha is not a function of z, so it just becomes ddz of this prime. So differentiate these ones, keep this constant, differentiate the other ones, keep the other constant. I mean, keep the first term constant. If you do this, you'll just get this blue term first, and then of course there is the rest, there is the other term, which is this. And also you need to apply product rule here also. So what you'll get is, you'll get for the next term, you'll get I alpha times what? U double prime phi plus u prime phi prime, something like this. Why? Because just use the product rule for this. You'll get an u double prime phi plus u prime phi prime. That's it. And then also we have the pressure, which is minus I alpha dp, or I'll just write it as phi hat prime. So this is what you get if you differentiate the x. Okay, if you differentiate the x momentum equation with respect to z. Okay, let's simplify certain terms, because I can see that some terms are getting cancelled. So this is I alpha u minus c times phi double prime plus I alpha phi prime u prime minus I alpha u double prime phi minus I alpha u prime phi prime. Okay, this is equal to minus I alpha p hat prime. So this term minus I alpha u prime phi prime and plus I alpha u prime phi prime cancels each other, which means I have I alpha u minus c phi prime phi double prime minus I alpha u double prime phi and this is equal to minus I alpha p hat of prime. And also I can cancel I alpha as well, which means the x momentum equation, when you differentiate this with respect to z, this comes out to be u minus c phi double prime minus u double prime phi. This is equal to minus p hat prime. Okay, so now what you need to do is, there is also this z momentum equation which we need to multiply it by I alpha. So this, if you do, this turn out to be what? This turn out to be, so it was, so I alpha times z momentum will give you what? This will give you there is an I alpha multiplied, and there is already this I square alpha square, it is already present. It is from this part. Okay, and then we have u minus c times phi, and then also I have the pressure gradient, but we need to first multiply it with I alpha, so there will be an I alpha term here as well. Okay, so this becomes minus I alpha times dp hat by dz. And then since we already cancelled the I alpha from this part, what you can do is, you can discard this I alpha and just write this as minus. So I square is minus 1, so this becomes plus, so this becomes alpha square u minus c phi equal to minus p hat prime. Okay, so what you just need to do is subtract these two equations. That's it, just subtract. You can appreciate that when you subtract, this p hat prime will just get cancelled. Okay, just subtract this. So let's name this equation. Maybe I'll call it as, let's see, what should I call it? Maybe I'll call it as 13a and 13b, and just do this 13a minus 13b. See, the objective is just to eliminate p hat. That's it, and that's why we are doing all this algebra here. Okay, so if you subtract this, what you'll get is u minus c phi double prime minus u double prime phi, and then minus alpha square u minus c phi and since pressure terms will just get cancelled, this is equal to 0. Okay, and I'll just rearrange these terms. So what you can do is you can take u minus c common, and then you can write this as phi double prime minus alpha square phi, and then this is equal to minus u double prime phi. This is equal to 0, and this equation that we get, this is one of the famous equation in flow instabilities, that is in instability of inviscid flows. This is known as your Rayleigh stability equation. This is known as your, it is named after Lord Rayleigh, and the name Rayleigh comes many a times in fluid mechanics, and this is also one of his contribution to the field. Okay, so this is your Rayleigh stability equation. Okay, where I hope you understand that phi double prime is d2 phi by dz, u double prime is d2 u by dz. Okay, so you can appreciate that this equation is homogeneous. So let's see the characteristic of this equation. So this equation is, first of all, it's an ODE. Okay, and this is a second order in phi, so this is second order, and also it is homogeneous. Now let's see that what are essentially the boundary conditions. So in this problem, the boundary conditions are there. So if we write the boundary condition, I just have, in principle, I just have two boundary conditions. Why? Because this is an inviscid problem, which means that I can't use the no slip boundary condition. So I just have one boundary condition which says that it's the no penetration boundary condition, which will just say that my so what it will say, it will just say that my w prime, which is a z direction velocity, this at this at z equal to 0, because we took the axis from the base, I guess. Let's one clarify. So let's see the physical picture once. Okay, so our axis was from the base. So the no penetration boundary condition will just say that the w prime at these 2 points is equal to 0. That's something that we get from the no penetration boundary condition. So what this will say is that my w prime at z equal to 0, 1, this is equals to, sorry, at 0, 1, this is equals to 0. But I have written w prime as w hat of z times e power I alpha x minus ct, which means that w hat at z equal to 0, 1, this is equal to 0. But I know that my w hat in terms of the stream function is what? It is, so w hat is equal to what? W hat is equal to minus I alpha phi. This means that since W hat is equal to minus I alpha phi, this means I can finally write my boundary condition as, so I can write my boundary condition as my phi at z equal to 0, 1, this is equals to 0. This is essentially the two boundary conditions that we have. Okay, I'll name this as, maybe I'll name this as equation 14. The Rayleigh stability equation, I name it as equation 14, and then this boundary condition as equation 14a. Okay, so this is precisely the no penetration boundary condition that I have applied here. Okay, this is your no penetration boundary condition. Okay, so I hope you understand that equation 14 is homogeneous, and we also found out that using the no penetration boundary condition, that the boundary condition is also homogeneous. So a homogeneous governing equation and a homogeneous boundary condition is basically an eigenvalue problem. It's kind of a recipe of an eigenvalue problem. So what we can conclude is that this is an eigenvalue problem. Okay, and what you need to do is you just need to find out this corresponding eigenvalue eigenpair. That is, you just need to find out phi of z, that is the eigenvalue corresponding to C, which is, sorry, phi of z is the eigenfunction. Okay, this is the eigenfunction corresponding to the eigenvalue C. Okay, this eigenfunction eigenvalue pair is just, so this is something that you need to evaluate by solving this Rayleigh stability equation. But you need to understand that it is not so simple to solve this Rayleigh stability equation, typically because this C is also an unknown here. Okay, and in fact it is very hard to solve this Rayleigh stability equation, and you can appreciate that the Over-Sommerfeld equation is much more easier to solve rather than the Rayleigh stability equation. There are multiple reasons why Rayleigh stability equation is little bit hard to solve, but but yeah, this is the case. So just, you can see the number of steps that we use just to get up to equation 14, which is just a single equation that determines how, the eigenvalue eigenfunction corresponding to C and phi uh, will evolve basically. Okay, and you just now need to solve this eigenfunction eigenvalue pair to know, and specifically this eigenvalue, because once you know C, see, the good thing is, once you know C, you can write your C as CR plus I times CI, and then once you know CI, you basically know the stability. You know the stability of the problem, because you know that if CI is greater than 0, it is unstable. Okay, and if CI is less than 0, it is stable. Okay, so all you need to do is just calculate this eigenvalue eigenfunction pair, which is governed by this Rayleigh stability equation. Okay, using this given boundary condition, which is, of course, it is homogeneous, and you just need to solve this eigenvalue problem to basically get this phi and C. You can appreciate that if you look back to your notes and see the derivations of the Over-Sommerfeld equation. In the Over-Sommerfeld equation, substitute RE equals to 0, and what you will get is exactly the Rayleigh stability equation, because you know that when RE equal to 0, we are in the inviscid region, and your Over-Sommerfeld equation reduces to the Rayleigh stability equation. Okay, so a special case of the Over-Sommerfeld equation, for in which the Reynolds number is 0, is nothing but the Rayleigh stability equation that we saw. Okay, all right. I hope this is clear. I'll stop here for a couple of minutes, and I hope this exercise is clear to you. Okay, so today is basically the last week of the interaction classes, but we will have another week. We'll have another additional week, because I have some more things to cover. And in that class, I will show you basically. So this is an eigenvalue problem, right? So we have not yet. So although we have derived the equation, we have not yet solved for phi, because ultimately we just need to solve for phi and C. So in the next class, I mean, in the extra class that we are going to have, mostly we'll have the extra class on Monday, this coming Monday, and then we'll call it a day of our interactive sessions. But on Monday's class, I will try to show you how to basically solve an eigenvalue problem. Okay, because then this analysis will be completed. But today, let's not go into much deeper details of this. But yeah. So this is the corresponding. So this is the given equation that phi satisfies. That is the Rayleigh stability equation. You can appreciate the number of steps that we use just to get this equation. Okay. So this equation itself is itself is so powerful, because see, this is just a single equation that determines how the perturbations will vary, because once you know phi, you can get your u hat and w hat, and once you know u hat and w hat, you know your u prime and w prime. But more importantly, instead of calculating all these things, the unknown that you mostly seek for is this eigenvalue C, because you just want to see that given there are perturbations, whether C will grow with time or C will decay with time. Okay, that is something that you guys need to understand. Okay, so so actually, I plan to cover three more things. That is how the Rayleigh stability equation determines the stability of the problem. But I guess we don't have that much time here. So what we'll do is, let's do one thing. Since we have done a lot of algebra this time, I'll in the next extra class, I'll cover three small topics, and then I'll show you how to basically solve an eigenvalue problem, and then we will we'll just summarize whatever we have learned, and we'll just call it a day. And this is going to be the agenda in the next class. But but yeah, so let's not start this now because this will be a new thing. So we'll learn something which is known as the Rayleigh inflection point criteria, and there is something which is known as the Jortov's criteria, which says, so basically it just says that if I have a given flow, how can I say that the given flow field is stable or unstable? Okay, this is or in other words, if I have a given base flow, from the base flow itself, can I assess the stability? And you can prove this Rayleigh inflection point criteria and the Jortov criteria from the Rayleigh stability equation itself, and that's why the Rayleigh stability equation is powerful. Even though you don't get the eigenvalue directly from by directly analytically solving this, but still you can do much more analysis on the Rayleigh stability equation to use these criteria to see that the given base flow is stable or not. And finally, we'll see something which is known as the Howard semicircle theorem, and and then I'll just show you one example on how to solve an eigenvalue problem, and I think this will be sufficient, for this for wrapping up this discussion sessions. Okay, but I appreciate you for watching these videos, and I hope this will be helpful for you to prepare in your. So first of all, it will be helpful for you to learn this course. I mean, that's the objective, that's the prime objective that one should follow and at the same time, this will help you to basically prepare you for your exam session. Okay, uh, so the discussions end here now. If you have any questions, you can ask me, or you can let me know. Like, if there is something else to discuss, you can let me know. So I hope you understood that how did we derive the Rayleigh stability equation, and from where we started, and these things, and yeah, you also need to understand the squares theorem, and you need to understand the essence of the squares theorem. Although we didn't prove the squares theorem, how did we convert the 3D problem into the 2D problem is something that you need to understand actually. So the proof of the squares theorem, if you are interested, I will post it in the discussion forum. You can drop me an email, or you can post the email thread in the discussion forum, and if you are interested, I'll show you the proof of the squares theorem. And basically, you need to just prove that your alpha tilde 2D is basically greater than the wave numbers in 3D. Basically, that's what you need to show. Okay, and yeah, that's the idea. So So what I'll do is, since we have a couple of minutes more, I will write down the Rayleigh inflection point criteria, but I'll explain this in the next class. Okay. So there is a criteria. It's called the Rayleigh inflection. Rayleigh inflection point criteria. Okay. And see, the Rayleigh inflection point criteria, uh, what it says is, so I'll write down the goal. So this will try to understand. So this will make you understand. So the goal is, what does, or you can say, how does Rayleigh stability equation predict about the stability of a given base flow? Okay, so this is something that we want to answer, and one of the criteria which answers this, which uses the Rayleigh stability equation. So the inflection point criteria can be proved from the Rayleigh stability equation, and it says that so the inflection point criteria says that necessary. So remember, it's not a sufficient, but it's a necessary condition for instability is that the base flow profile must have an inflection point. Okay, this is what the Rayleigh inflection point criteria says. Okay, and so I hope you know that if my u of z is the base flow, if my u of z is the base flow, then at the inflection point, I think you know what is an inflection point means. Then at inflection point, I know that my u double prime at, let's say, z equal to z naught, where z naught is the inflection point, is equal to 0, where this z naught is the inflection point. Okay, so I hope you understand that if I have, let's say, a velocity profile, let's say of this form, let's say of S form, okay, then I think you understand that when I move from this point to this point, the curvature of the curve changes. So this indicates the presence of an inflection point. Okay, so this is basically an inflection point. Okay, and we have discussed this in the boundary layer theory also, when we saw that the presence of an inflection point is essential for boundary layer separation. Okay, that is something that we saw, and here also we notice the usefulness of an inflection point. But yeah, what the Rayleigh inflection point criteria said is that if the given base flow have an inflection point, then it is a necessary condition for the flow to be unstable, but you cannot guarantee that the flow will be unstable. Okay, think about it. For instance, if I have a Couette flow, apply the Rayleigh inflection point criteria, and think about like whether a Couette flow is stable or not. Okay, I'll leave you as an exercise to think. We'll discuss this further in the in our next meeting, that will mostly be on Monday. That will be an extra. So this ends the normal regular interactive sessions. But since we have couple of little more things to cover up, we will we will also meet on Monday from 3 to 5, and you will a priori be posted about Monday's class if it is fixed on the, I mean, in the course website, and also by emails. But if we meet on Monday, we'll discuss more on this Rayleigh inflection point criteria and the questions that I asked. And does it guarantee stability? And are there more stability criteria required? And finally, we'll try to see how to solve an eigenvalue problem and end the discussion on this point. Okay. I thank you all for attending and watching these videos. Keep learning, and maybe hopefully we'll see each other on Monday. Thank you.